Hello guys, welcome to another easy LeetCode question. Today we're going to solve path sum. So you're given a binary tree and you should check whether there are branches in this tree that add up to a target sum. For example, a binary tree branch could be something like this: 1, 2, 4, this is a branch; 1, 2, 5, this is a branch; 1, 3, 6, 1, 3, 7, this is also a branch. So you should check whether there are any branches in this tree that add up to a target sum, and return true whether there are branches that add up to a target sum, or return false if there are no branches or no paths that add up to a target sum. So this question is quite similar to the branch sum question that we have in this channel, just that this one's a little bit lower in the simplicity hierarchy. To solve this question, we're going to traverse the binary tree in a depth-first search way, targeting every branch, adding a running sum as we go through each node's value, and whenever we get to a leaf node, we check if our current running sum is equal to the target sum. So we stop adding when we get to a leaf node because a leaf node signifies the end of a particular path or branch. So if you don't know what a leaf node is a binary tree node that doesn't have other children nodes attached to it. For example, 4 is a leaf node, 5, 6, and 7, all of these are leaf nodes because they don't have other children nodes attached to them. All right, so fair enough. Let's go through an example so you can see exactly how the solution works. Take, for example, you're given this binary tree of nodes 1, 2, 3, 4, 5, 6, 7. And you should check whether there's any path in this binary tree that add up to the target sum 8. So what we're going to do is we're going to initialize a running sum, and we're going to traverse this tree in a depth-first search way, specifically in a pre-order traversal manner. So we visit a node, and then we visit its left and right children nodes. So let's say we've called our depth-first search function, and we're at node with value 1. So initially our target sum is going to be 0, but when we visit node with value 1, we add that value to the target sum, so 0 plus 1, so it's 1. So the running sum at node with value 1 is 1. So now our current running sum is 1. And then we call the DFS algorithm on the left child of 1, and then we get to 2. So when we get to 2, we add 2 to the current running sum that we have, which is 1. So 1 plus 2, that's 3. So our current running sum is 3. And then we call the DFS algorithm on the left child of 2, going to 4. And then we add 4 to the current running sum that we have, which is 3. So 4 plus 3, that's 7. So our current running sum is 7. Now we go to the left child of 4, which is this, but oh wait, it's null. And then we check if its right child is also null. And left child's null, right child's null. So now we know that 4 is a leaf node. So whenever we get to a leaf node, we check if our current running sum, which is 7, does it add up to the target value, which is 8? No, it doesn't add up to the target value, which is 8, so we haven't found an answer yet. So we move back up the recursive tree up to 2. So from 4, we go back up to 2. And then we call the DFS algorithm on the right child of 2. So at 2, our running sum at 2 is 3. So when we call the DFS algorithm on the right child of 2, we're passing 3 as a running sum. We're not passing 7 as a running sum because we've moved back up the recursive tree. So when we get to 5, which is the right child of 2, we have 3 as a current running sum, and then we add 5 to 3. 5 plus 3 is 8, so we have 8. But oh wait, we've actually found an answer, but our algorithm's really stupid, doesn't know that we found an answer, so it's going to run all the other computations that we have in the algorithm. So from 5, we call the DFS algorithm on the left child of 5. Oh wait, it's null. We call the DFS algorithm on the right child of 5. Oh wait, is null. So 5 should be a leaf node. And then we check if our current running sum 8 adds up to the target sum, which is 8. And of course it does, so we just return true. All right, so this is how you solve the path sum question. So what's the time and space complexity of this algorithm? Well, for time complexity, it's fairly simple because we're going through every single node in the binary tree. So that would be O of n time. If you want to get tighter bounds for time complexity, you might say it's O of 2 to the power d, where d is the depth of the binary tree, because the binary tree has at most 2 to the power d nodes in it, since every node has 2 children nodes. And then for space complexity, because of the recursion, we're storing frames on the call stack, which would have it at most O of d frames on the call stack. So space is also O of d, where d is the depth of the binary tree. You might also argue that this is not always the case if you take into account the concept of tail recursion, where if the recursive call is the very last thing that you do in the function, it might make the recursive frames in the call stack obsolete. So that's also like a very academic kind of explanation. I really recommend you look it up. It's going to give you cool guy points in the interview. So yeah, let's dive into the code for this question. All right, so the first thing we want to do is to write our recursive DFS function. So I'm going to call it public DFS, and it's going to take in 3 arguments. The first one is a tree node. I'll just call it root, and then the next one is target, and then the next one's going to be our current running sum. So let me just call it running. So now that we have this, what we can do is we can write up our base case. So if root is equal to null, we just return false. And then if this is not the case, it means we have a valid value in the root, then we can add that value to our current running sum. So we can say running is equal to running plus root.value. And then after this, we have to check if we're at a leaf node. So we can say if root.left is equal to null, meaning if it doesn't have a left child, and root.right is equal to null, doesn't have a right child. So if this is the case, it means we're at a leaf node, and then we can check if our current running sum is equal to the target sum, and then we just return that answer. So we just say return whether running is equal to target. So that's it. So now that we've taken care of that, we have to call the DFS algorithm on the left child and also on the right child. So what we can do is we can also return DFS on root.left, and now our target value is still target, and then running, since we've already incremented running, so running remains the same. Or so I think naming it DFS is kind of like misleading. It's not really verbose, it's not really readable. So let's call it has path sum. So we're checking if the left path has the path sum, and we're also checking if the right path has a path sum. So it has path sum, root.right, same target, and same running. So that is pretty much it for this DFS function. All we have to do now is to call it in the main function. So here we're also going to do a simple error check and say if root is equal to null. If this is the case, I think we should just return false. Here we just say return has path sum, pass in the current root, and the target is sum. And our current running sum is going to be initialized to 0. And that's it. Let's run this and see what happens. This should be public boolean because we're returning a boolean value. Let's run this again. Cool. Let's submit this. And yeah, it's successful and it's really fast. So that's how you solve this question. As you can see, I've solved this question a bunch of times. The first time I solved it, I think it was last year. So this was the first question that gave me a lot of difficulty when I was just starting up with algorithms and data structures. And I remember I couldn't figure it out. I looked at the solution online, but then I couldn't figure it out. So that's it. 1 year later, I think I know a little bit about algorithms and data structures. I'm always getting better. And if you're just starting off like me, please don't give up. The first time, you cannot even solve the two-sum question, I'm going to tell you that. But as you keep solving more and more questions, you're going to pick it up on the way. And as you can see, I've tried different variations of this question, different variations of the solution. Some of them worked, some of them didn't. But yeah, So if you like this type of content, please consider subscribing to the channel, comment down below if you have something to say, smash the like button for the YouTube algorithm, and I'll see you in the next one. Bye bye.